This section is called Antiderivatives. And what we need to know is very little compared to how dense some other sections were. However, this section is very important and is the basis for what we're going to learn on chapter 5. So we have the definition of an antiderivative and a theorem that we're going to be using for the rest of the section. And you're going to see that it is not going to be so difficult to find actual antiderivatives of functions. However, there are some things that you do need to consider, and you do need to be careful to separate what you're going to learn today from what you already know. And I can see how it can get a little bit confusing because we have already done derivatives for a long time. So to do antiderivatives, you might get some concepts a little crossed there. So let's start with a very simple example. Let's say that I have a function f of x equals x squared. So you know this function, it's a parabola, and it has an absolute minimum at 0, and then it decreases and then it increases. So what we want to find is not the derivative of x squared, because we know that f prime of x is 2x, and this function right here describes the slope of every single point in this parabola. We don't want to find that anymore. When we're finding antiderivative, we're finding something else. We're finding some function that for the rest of the section we're gonna call capital F of x. Some function right here, so that the derivative of this gives me x squared. So I know what you're thinking. I know that it has to be a cubic function, for example, x cubed. And I know that when I take the derivative, it gives me x squared. However, it does not give me exactly x squared. When I take the derivative, let's say that I have a function that is x cubed, you know the derivative of this will be 3x squared. However, how am I going to be able to get just simply x squared? Well, if you know that the derivative of x cubed is 3x squared, then there's got to be some number in here dividing this, so that ultimately when I take the derivative, it will cancel out. So you realize that to have a 1 in front of the x squared, the number that needs to be divided in this function is 3, because you know that the 3 in here is going to come down as the coefficient of x squared, and 3 over 3 is 1. So the function, the antiderivative of x squared, is the function x cubed over 3. Why? Because when I take the derivative of this function, it would be 3x squared over 3. Remember that the constants that are multiplying just multiply along the derivative. And 3x squared over 3 is simply x squared. So this and this absolutely match 100%. Okay? So antiderivative of x squared will be x cubed over 3. But this is only one of them, because I know what you're thinking. I know that if I have this function x cubed over 3 plus 1, the derivative of this will be 3x squared over 3, and the derivative of 1 is 0. So I know that this function that is different from this one, also the derivative gives me x squared. And so it would be the same for x cubed over 3 plus 2 plus 3 plus 4 plus 5, or minus 1, minus 2, minus 3, minus 4, minus 5. As long as I'm adding or subtracting a constant, then the derivative of this would always be simply x squared, and I'm not adding anything else or subtracting anything else. Now notice how this function, if I want to add an x to it, that will not be an option, because when I take the derivative of this, the derivative in here will be x squared, and the derivative of x will be 1, and x squared plus 1 is not the same as x squared. So please start forgetting about crazy things like that. The only thing that I can do to obtain a different antiderivative from the one that I originally thought is to add or subtract a constant, and that would be the only thing that I can do. Notice how if the antiderivative is x cubed over 3, that will be the graph of x cubed over 3. If I move it up or down, x cubed over 3 plus x cubed over 3 plus 2, or if I bring it down 2 units, x cubed over 3 minus 2. At every single x, the derivative or the slope of the tangent line hasn't changed, and it keeps the same value. But if I move it in this direction, if I move it horizontally, then that's not really the case, because, for example, let's say that I move my x cubed function here. So now the derivative at this point, you know, it's 0, but if I go to this graph, it's no longer 0. I mean, it's giving me some certain value. So it only matches my antiderivatives, it only matches with my original function as long as I'm adding or subtracting a constant to the entire function. So at the end, in general, what we're going to say is, if I come up with some antiderivative, the most general one, I have to add some constant, because I know the derivative of this, if I want to take the derivative of this entire expression, will be simply f prime of x, and the derivative of a constant is 0, which is exactly what f of x is. So you can think of this function as the derivative of this function is the original function. So we're going to start working backwards here. Let's look at example 1, where we have to find some antiderivatives. And the table for all the formulas is given on page 345. And you can see that there are some formulas for you to apply. And there's going to be some other formulas that we need to actually look at a table of antiderivatives. But, you know, from exercises, you're going to be able to memorize them. So now I have a function sine of x. I know that you will be tempted to say, oh, right away, cosine of x, but no. You're finding the antiderivative of f. So you're finding capital F. You're finding some function for which you take the derivative and it gives you the original. So you know that it's not going to be simply cosine of x, because you know the derivative of cosine is negative sine, but you don't have negative sine, you have positive sine. So the only way to cancel out that effect of the negative is by making this expression negative. So now, how do you actually check your answer? Well, find f prime of x, and if f prime of x gives you the original function, then you're correct. So the negative 1 is a constant. It's a constant multiplying the function, so I can just keep it. And then the derivative of cosine is negative sine. So because this is true, negative times negative is positive, so this is sine of x. So you have found the antiderivative, or one of them, of sine of x. Since the direction says that you have to find the most general one, your answer is not complete until you put plus c. What if you forget to put plus c? Then you're not given the most general antiderivative, you're just given one of them out of a gazillion. So it is very important that you end your answer with plus c. Now, how do you know how much is c worth? Well, in here, in this example, they are not giving you that information, but later on we will see when how the problem looks like when we have to figure out how much c is. But for now, the most general includes a constant that you don't know how much it is, and you're not asked to figure out how much it is yet. Now, for this one, you know that, and this is from the derivative part, you know that when you have the derivative natural log, that is 1 over x. So you're thinking that this has to include some logs, and that would be correct. So this antiderivative of f is going to be natural log of x. However, you have to be careful, because while this is true, you don't know whether 1 over x is positive or negative. You remember that this is a function. It's it's a rational function, and it has two branches, one for when x is positive and one for when x is negative. So when you're taking a natural log of something, you have to make sure that the inside is positive. So we're going to add absolute value here. And because of that, then now we are considering both options. X could be positive or x could be negative. And now, right now, we're just taking the natural log of a positive value always. And again, your answer will not be complete until you add plus c. And now for this one is trying to get you to think about what would be the general idea of finding the antiderivative of x to the something of some power of x. For example, remember the example that we just did. The antiderivative of x squared was x cubed over 3. So because ultimately this 3 that comes in front needs to be cancelled out so that you have a 1 in front at all times. So that and the same thing will happen with others. Let's say that you have x to the 4th. You know the antiderivative will be x to the 5 over 5, because when this 5 comes down in front, when you take the derivative, then ultimately you want it to cancel out with a 5. So when you have x to some power, the antiderivative would be, the power increases by 1 now, so it would be x to the n plus 1, and then the coefficient you have to divide it by that n plus 1, as long as n is not -1. And we say that because x to the -1, you know, is the same as 1 over x, and the antiderivative has nothing to do with the power of x. The antiderivative has to do with natural log. Because imagine if you do if you replace -1 instead of n, you will have x to the -1 plus 1 over -1 plus 1. It would be x to the 0 over 0, which is not an antiderivative of this function. So I'm going to find the antiderivative of x to the n as long as n is not -1, and that will be x raised to the power of the exponent plus 1 over that exponent, and plus c because I'm finding the general function, and again say that n cannot be -1. For example 2, it says find all the functions, so that implies that you have to find the most general antiderivative. It says find all functions g such that the derivative is this. So if you're trying to find the original function knowing the derivative, what you're finding is the antiderivative. So we know the derivative of g. We need to find g by using antiderivatives. So we're going to use antiderivatives. So now let's look at the function g. Since we have a plus, then I know that I can find the antiderivative of this and find the antiderivative of that, and then the sum will be an antiderivative of g prime. So when I do that, the second part looks a little bit more complex than the first part. Now let's just remember that the easiest thing to do is for me to distribute the x's so I can have a sum of powers of x rather than having something like this, because the way it is right now, it's going to be very hard for me to find some function whose derivative gives me something looking like that. Unless I mean, I'm thinking it could be some kind of quotient, but it would be terribly time-consuming to find some kind of quotient. Remember that you will have to figure out top and bottom whose derivative comes out to be this way. So leave it alone. It's impossible. Just don't do it. Write some powers of x, and then you will be better off, because so far that's what we know too. All right, so let's find the most general solution for this function. Let's find what is the function g knowing the derivative. So g of x will be some function whose derivative is 4 sine of x. So the 4 I keep, and remember that if I want the derivative to be sine, then the antiderivative is negative cosine of x, because when I take the derivative of cosine, that gives me a negative number that is going to cancel out with this. Plus, now I have to rewrite this in some way so that I can find the antiderivative easily. So let me just rewrite that right here. 2x to the 5th over x, that will give me 2x to the 4th. And then this is x to the 1/2 over x. You just subtract the exponents, 1/2 minus 1. That will be negative 1/2. Now I can apply, since the exponents are different from -1, I can apply the power rule for antiderivatives. So I know that the exponent is going to grow by 1, so it's going to be x to the 5th, and I know that I have to divide by that number. Since the 2 was with the x to the 4, the 2 stays because it's a constant multiplying that. And you will see that if I take the derivative of this, would be the 5 will come in the front, cancel out with this 5, and I'm going to have 2x to the 4th, which is what I have originally. And now I'm going to apply the same rule here. The negative 1/2 is going to grow by 1, or I'm going to have to add 1, and that will be positive 1/2. So it's going to be minus x to the positive 1/2, and I'm going to divide by positive 1/2. And the cherry on top, cherry, see, genius. The cherry on top plus a constant. Now let's just rewrite this in a friendly manner. So g of x, in general terms, in here all of them are counted. If you don't put the c, this is one of the antiderivatives. When you put the plus c, you are counting them all. It will be negative 4 cosine of x plus 2x to the 5th over 5. And then remember that dividing by a fraction is the same as multiplying by the reciprocal. So dividing by 1/2, that's the same as multiplying by 2. And plus c. And then that will be your final answer. Beautiful. In example 3, we're going to have to use one of the formulas that they give us, which is actually, it's not so difficult to figure it out. We have learned from derivatives that the derivative of arctangent is 1 over 1 plus x squared. So when you read that table of derivatives, instead of left to right, from right to left, that is the antiderivative table that we have here. So we're just, if this is antiderivative, that just means backwards. We're going to be able to use this formula on page 345. Those are the formulas that you have to be familiar with. So again, we know the derivative of f. We have to find f. So to do that, antiderivatives again. And the difference of this problem compared to example 2 is that we are given some initial condition. Or some kind of condition. It doesn't have to be initial condition. It's called initial condition because they are giving you the value of the function at 0. But initial condition, this could be a situation of a particle moving where time starts at 5. So it doesn't mean that it has to be at 0. They could give you f of 3 equals 10 or something like that. So there is some kind of initial condition. There is something that you know about this function, because you know that this function, you have many options for it. But by knowing the function crosses a particular point, then you are making sure that you're just picking one. If you compare it to problem here, example 2, this is the general g. But if they say, if you know that g of 1 is 2, then you can replace x in here for 1, equal this to 2 and figure out how much c is. And that's the idea. That's going to be the idea here in this problem. After we find the general, then you can replace this information to find out how much is c. So this implies you need to find c. Okay, you need to know how much that constant is. All right, so again, I have a sum, so I know that I can find the antiderivative of each. So I know the antiderivative of e to the x, which is e to the x, because I know the derivative of e to the x is itself again. So that was easy. Now this is 20 times this expression. You know that this will be 20 over 1 plus x squared, because the exponent is -1, that implies reciprocal. This is also the same as 20 times 1 over 1 plus x squared. So as long as you are multiplying, you can use the formula on page 345, and I know that the antiderivative of this is this. So the only thing in here, you're just going to have a 20 in front of the arctangent of x, and that will be the only difference. Since you know that you can split this into something like this, I know the antiderivative of this, so that antiderivative will just be multiplying that 20. So plus 20, the arctangent of x. And then the general solution, don't forget to add the cherry on top, plus c. So there is infinitely many f's that whose derivative is this particular function right here, but there's only one of them, so that when x is 0, f is -2. So f of 0 will be e to the 0 plus 20 arctangent of 0 plus c, and that you know is -2. With everything in here known except for the c, you're able to find how much c is. E to the 0 is 1, arctangent of 0, for what angle in radians? The tangent is 0, and that's 0, times 20 is 0. 1 plus c is -2, so c is -3. Since they are asking us to find f, the only thing that I have to do now is replace c for -3. So the function in particular is e to the x plus 20 arctangent of x minus 3, and that will be my answer. There is no constants anymore. All the other options for functions whose derivative is this, the only one that goes through the point 0, -2 is this one.